Hello everyone and welcome to today's explainer, Basic Construction Materials Part 1, focusing on bricks, stones, cement, and aggregates. I'm going to be your professor today as we explore the literal building blocks of our modern world. Now, right off the bat, I highly recommend turning on your English subtitles. We're going to be covering some very specific industry terminology that you absolutely need to nail down for your exams. And honestly, seeing the words right there on screen is going to help lock them into your memory. All right, let's dive right in. Here's our syllabus for today's explainer. We'll start with the civil engineering context, move into bricks and natural stones, then cement and aggregates, follow up with material contrasts, highlight some common errors, and wrap it all up with a final review and quiz.
Section 1. Civil Engineering Context. Before we look at the materials themselves, we need to understand exactly what they're supposed to do.
As a structural engineer, your fundamental perspective always comes down to load-bearing capacity. I want you to think of this like a highly coordinated relay race of forces. Every single ounce of weight, whether it's a dead load like the actual weight of the building or a live load like all the people walking around inside it, has to be safely carried down into the earth. The race starts up at the slab, which passes the baton to the beam, transfers the load down the column, pushes it into the foundation, and finally safely disperses it into the soil. The basic materials we're about to look at? Well, they are the athletes running this exact race. Section 2. Bricks and natural stones. Let's look closely at our primary foundation blocks. When it comes to masonry, your site conditions entirely dictate what material you choose. Take manufactured burnt clay bricks, for instance. They're molded and kiln-fired, which gives them a wonderfully uniform shape, great fire resistance, and makes them very economical. They're absolutely perfect for standard partition walls in local residential builds. But natural stones? They are a different beast entirely. They possess incredible hardness and massive compressive strength. You simply wouldn't use brick for heavy weathering. Instead, you'd select a high load-bearing stone for critical infrastructure. Think massive bridge piers or heavy retaining walls.
But to pick the right stone, you really have to understand its geological origin. Try to picture the intense natural forces that actually forge these materials. First, you have igneous rocks, like granite and basalt. These are born directly from volcanoes, so they are incredibly dense, hard, and crystalline. Next up are sedimentary rocks, like sandstone and limestone. These are formed over thousands of years by layered grit and immense pressure. And finally, we have metamorphic rocks, like marble and slate. Essentially, these are older rocks transformed by intense heat and pressure deep within the Earth's crust. Each of these classifications dictates the stone's engineering properties, from its porosity right down to its abrasion resistance.
Section 3. Cement and aggregates. The concrete composite.
If bricks and stones are the traditional building blocks, concrete is the ultimate composite material. Let's look at the chemistry of its structural glue, ordinary Portland cement, or OPC. Cement is made by grinding a fused material called clinker with just a touch of gypsum. It's honestly a lot like baking a cake. The performance relies entirely on exact chemical ratios. Notice the top two ingredients. Lime, making up roughly 60 to 67%, is the absolute most critical element. It drives the overall strength and soundness. Then you have silica at 17 to 25%, which combines with the lime to create calcium silicates for long-term durability. These are strict industry standards, and they are strict for a very good reason. So that's the glue. Now let's talk about the skeletal bones, the aggregates. We separate fine and coarse aggregates using one very specific standard, the 4.75 mm IS sieve. Picture a standard kitchen colander. Fine aggregates, like river sand, pass right through those holes. They fill in the microscopic voids and improve the mix's workability. But because they have a higher total surface area, they actually require more water. Coarse aggregates, on the other hand, like crushed stone or gravel, get trapped in the colander. They provide the massive bulk and the primary compressive strength of the concrete while needing significantly less water. Finding the perfect balance between these two is the true secret to an optimal concrete mix.
Section 4. Material contrasts. How do these compare to other structural options?
Okay, so basic materials like stone and concrete are absolute masters of compressive strength. They are fantastic at bearing heavy, crushing downward loads. But what happens when site conditions demand something else? That's where structural steel and wood come in. Steel offers phenomenal tensile strength, ductility, and elasticity. If a building is going to face dynamic, unpredictable lateral forces, like hurricane winds or earthquakes, steel allows the structure to bend and sway without just snapping. Wood, alternatively, is incredibly lightweight, has moderate bending strength, and offers gorgeous aesthetic appeal. assuming it's properly seasoned to prevent shrinkage, of course. A master engineer knows exactly when to rely on the massive compressive power of concrete and when to pivot to the flexible, high-tensile nature of steel.
Section 5. Common errors. The design pitfalls you absolutely must avoid.
Now, theoretical knowledge is great, but it doesn't always translate perfectly to the job site. Let's look at a few critical pitfalls, and I'd pay close attention because these will definitely show up on your exams. Error number 1, allowing excess lime in your cement mix. Yes, lime provides strength, but too much of it directly causes cement unsoundness. That means it will dangerously expand and crack after setting. Error number 2, choosing a weak, highly porous sedimentary stone for high load-bearing bridge foundations. It will rapidly degrade under hydrostatic pressure. And error number 3, ignoring that 4.75 millimeter aggregate threshold. If you mess up your fine-to-coarse ratio, you drastically alter your water requirements. That ruins your water-to-cement ratio and fatally compromises the structural strength of the entire pour.
Section 6, Final Review and Quiz. Let's lock in what we've learned. We've covered a lot of ground, so consider this your ultimate study sheet. Remember the structural load path: slab to beam to column to foundation to soil. Know your stone origins: igneous, sedimentary, and metamorphic. Memorize that OPC chemistry. Lime at 60 to 67% is your primary strength driver. And finally, never forget the aggregate standard. The 4.75 millimeter sieve is the strict dividing line between your fine void fillers and your coarse, strength-giving bulk. All right, let's finish up with a quick pop quiz to test your understanding. Based on everything we just discussed, what specific structural failure occurs if there is excess lime in ordinary Portland cement? Take a second. If you said unsoundness leading to expansion and cracking, you hit the nail on the head. It is pretty wild to think about, right? The microscopic chemistry of lime and silica literally dictates the massive structural safety of the skyscrapers we live and work in every single day. So, how will you apply these foundational rules to your next big design project? Study hard, everyone, and I will see you in our next explainer.